Hello, everyone. My name is Lulu, and I'm here with Stephen, Bao, and Devang, and we are Team 404. And today we are here to present our design. It is annoying to carry around a bunch of keys. Keys can come in many shapes and sizes, but that does not change the fact that carrying keys is heavy, cumbersome, and downright annoying. We can all agree that our keys are often the most lost, misplaced, and disorganized item. They get tangled up in our bags and are constantly rattling in our pockets. Solving this problem would be a digital system that stores a key onto itself like a door lock that requires a pin. This is great, but that does not solve the second problem, having to remember the PIN and the time wasted punching in the PIN. A facial recognition door locking system solves both of these problems. It saves time, is a secure system to keep away intruders, and practically seamless. With the idea in mind, we set out on designing and creating an affordable compact of our facial recognition door locking system and packs a punch against the. Scouring the internet for trending technology, we found many quality of life improving devices. At the time of the research, we found that there were a large section of the population interested in custom ergonomic mechanical keyboards, smart coffee makers, and facial recognition door locking systems. We decided to stick to the facial recognition door lock system as we believe that there will be a larger target audience in comparison to the other two choices. We concluded our target audience are in the residential area. After looking into our choice, we conducted more research in our local area and we created an online survey where we described the product, its uses, and capabilities. 93.11% of the survey respondents replied that they would likely purchase this product.
My name is Steven, and this is Team 404's project on our facial recognition door locking system. Early marketing research we went off and brainstormed some ideas. With those brainstorms, we had some early brainstorming feasibility issues, such as demonstrating image recognition, demonstrating a successful recognition in low light conditions, and to see if our Jetson is able to communicate with our integrated lock. Well, our first feasibility issue is to demonstrate image recognition. The issue with training the Jetson Nano is creating a good enough machine learning algorithm. The algorithm will need an immense amount of labeled data to accurately take in data of a person and make the decisions of whether the object presenting itself in front of the Jetson Nano is a person or not. If the Jetson Nano is able to identify that the object is a person, then it is required to run through its database and see if it recognizes the individual's face. A recognized face will gain access, while other conditions that fail will be locked out. There will be cases when, in training and testing, false positives and false negatives. Furthermore, the amount of time it will take for the embedded system to train itself on a person's face. There is a very good chance that the likelihood of these issues will arise during a demonstration. This is our main attraction, so the impact on our project will be critical. To mitigate some of the risks, we must understand the development environment of the Jetson Nano, gather the data, and modify the data for the Jetson Nano image recognition. Classifications of the image as something like insert name or not insert name is required. During the training, the ideal model needs to be created to ensure overfitting and underfitting does not happen. To mitigate overfitting and underfitting, we must find and create the ideal model with perfect variables that make the model perfect for this situation. Another method is the ratio of the data being used for training and testing data. A good ratio could be 80% training and 20% testing. Another good ratio would also be a 50-50 split. Our objective is to recognize the faces of the individual within the dataset after being trained. Each person within the dataset will be labeled with a name corresponding to them. Those who are not recognized will be labeled as unknown. A feasibility issue during early brainstorming is demonstrating low light image enhancement. A potential issue could be how one presents the embedded system an image into the AI model. The lack of lighting could not provide enough sufficient information for the embedded system to be able to recognize the image, let alone a user. The likelihood of this appearing during demonstration would be highly likely. The impact it will have on our project would be severe, as this is another feature of our design. To mitigate the risks here, we need to help make it easier for the AI to understand the image and figure out if it's a user. The first idea that comes to mind is training the embedded system in low light conditions, where it takes the image and brightens up the image so that it is similar to daylight conditions. There are multiple methods to assist the AI in its task. Methods such as converting the image it receives from RGB to grayscale, equalizing the received image histogram, applying a Gaussian filter, and a histogram of oriented gradients. Are all methods one could use to help the AI in understanding the image and figuring out if it's the user. To demonstrate the algorithm works, we will have a picture on a screen to show an example of our source image, the Brighton image, and its confirmation. Our objective is to recognize the faces of the individuals within the dataset in low light conditions after being trained. Low light, defined by us, is an area that is lit with about 350 lumens. Each person within the dataset will be labeled with a name corresponding to them. Those who are not recognized will be labeled as unknown. The image within the dataset will be taken by the embedded system. This input image will be put through an enhancement algorithm and produce an enhanced image.
Hi, this is for embedded system. We use Jackson Nano from NVIDIA. The embedded system holds our software and acts as the main hub for communication among the other subsystems. The duty of embedded system is to send and receive signals from the other subsystem, as well as executing its own duty, such as running code to process an image. We use IR camera for our project. The camera provides the embedded system its data to tell whether or not the user who is in front of the camera is an authorized user or not. It also sends the data to embedded system to send a signal to turn on or off the IR camera LEDs to help assist itself in low light conditions.
For the custom PCB, we created two PCBs. One is motor driver and other one is LED array. Motor driver is used for lock and unlock the door dashboard, and LED arrays indicate successful and unsuccessful door lock and unlock. For the motor driver, we use L293D is H-bridge, LM785EE is a linear voltage regulator, 1 microfarad capacitor, 3-pin header, and 3-pin header, 6-pin header, and J. As you can see on the PowerPoint, we have on right hand side we have a diagram of our custom PCB, and on the left hand side we have a layout of our custom PCB board. And for the LED arrays, we use red and green LEDs, 10K resistor, 330K resistor, and P2N2222. For the user interface, we put the red physical button to lock the door from the outside. When you leave, it's depending wherever you put. And red and green LED indicates user that if it's a LED turn green, the door is unlocked, and if the LED turns red, the door is still locked. Due to the coronavirus, we couldn't print our 3D part, but we still have our design. For the 3D print, we decided to print two different designs, one for our embedded system, one for IR camera. On embedded system box, on the side wall, we have a pentagon shape cut holes for ventilation to get rid of the hot air inside the box. We also have an I/O cutout on the other side to easy access for I/O pins. We also implement hinges in the design to access our internal parts easily. There is a slit made on the side to camera ribbon cable to go through. For the IR camera, we dedicated enclosure for camera, and it's all separate from the main body enclosure. Thank you.
Our embedded system, NVIDIA Jackson Nano, is the main hub for communication across our device. A camera is connected to the Jackson via a ribbon cable, and it communicates with Jackson through the camera serial interface. Communication is received whenever there is a user in front of the camera. The image is sent from the camera and into the Jackson to compare the image with its image database and image libraries. Whether or not there are not matching in images within the database to authorized or unauthorized user. The Jackson will send a signal to LED array PCB via its GPIO pins. If user is unauthorized, it sends a voltage to array of the red LED. If the user is authorized, it sends a voltage to array of green LED. Furthermore, in the case of an authorized user, the Jackson will send more signal, such as one to the motor driver PCB to drive the motor within the interray clock to open the dashboard. From the camera image, the Jackson is able to detect the brightness of environment. If under threshold of the amount of lumen in the surrounding area, the Jackson will send a voltage through its GPIO pin to array of IR LED and help them illuminate the environment to access the camera in seeing in low light conditions. Additionally, connect to our motor driver PCB is a push button to clock the
few machine learning tools that we use. Our main machine learning tool used for our facial recognition door lock system is the open source library Open Computer Vision, or OpenCV. OpenCV assists our embedded system by providing the libraries with optimized algorithm to detect facial objects such as mouths, eyes, and noses. Furthermore, it is able to track human movement and differentiate it from other movement, from organic and inorganic beings. The most important part of OpenCV library is the ability to find similar images from an image database. This greatly helped our facial recognition programs. Working together in tandem and supporting OpenCV or other Python libraries, another big assistant was Pillow Imaging Library, or PIL. PIL has the capabilities to adjust an image contrast, brightness, or color. We use this to our advantage when we take an image. We transform the image from a color to grayscale format to save storage data. PIL also allows for text displayed on an image. This helps us in assigning names to users for labeling, testing, and debugging throughout our project. Another piece of the pie used was the NumPy library. This allowed us to use large multi-dimensional arrays and matrices, along with high-level mathematical functions to help calculate them. We used NumPy together with PIL to separate the hue, saturation, and vibrance data collected from the image. They're separated into H, S, and V. Only using the vibrance array, we output the array to a single value, creating a threshold using the value to determine if the IR LEDs will turn on or off to assist the camera to take a clear picture during low light conditions. Our last machine learning tool is threading. Threading allows for multiple tasks or functions to run without having to be queued. Instead of waiting for a task or function to be executed before it's their turn, they just run alongside each other. Threading improves our stuttering issues with our camera. Every time the camera would take in data, it would wait for the authorized process to complete, then the unlock process before it would take in another image. This bogs down our efficiency, but threading allows each task to run separately from each other.
There are a few lessons learned throughout the project. A major lesson learned was not to solo a task. Oftentimes, we found that splitting and working in a two-man team was more efficient. There were cases where one of us was not able to understand a concept and the other did. Instead of getting stuck and not progressing, the one that understood would explain the other in the concept in terms we both could understand. This was apparent because our native languages was not English. A minor debugging lesson we learned was to make sure that the connection was secure before conducting tests. We had a few headaches wondering why our program was not working, and it happened to be things such as the ribbon cable not connecting to the IR camera and the embedded system was not securely connected to the CSI ports. Sometimes we would get the errors within our Python code and it was due to tab spacing. A lesson for us was to use comments also on the code. We were fortunate enough to code in Python because where the language is for the most self-explanatory. And if we decided to code in anything else, such as like C or Java, we would have been in big trouble when we passed our code to each other or when we had to come back to our codes after like long extended breaks. There are a few aspects of our project we wish we could improve, but due to our limited knowledge, limited budget, and time constraints, we could not commit to them. The first improvement we would like is for a wider field of view, which is the FOV, to receive more information of the surrounding environment. After multiple tests, we had a hard time fitting 3 or more people's faces in front of the camera for a facial recognition. A big security flaw of our system is that it is easily able to be spoofed with something as simple as an image printed on a sheet of paper of the authorized user. As another wanted upgrade, if we had the budget, time, and resources to increase the security, we wanted to implement the use of dot projection for a more accurate and secure method to scan for users. Dot projection places an array of dot-shaped light on the user's face to determine the depth of the user's face, so that a simple image on a sheet of paper could not bypass the system. Due to time constraints, we were not able to implement our initial idea of creating a mobile application to add as a feature to unlock the system. We could not even add a digital screen to act as a number pad through which you can use the pen. Other than the upgrades listed above, we wish that we'd had more time to buffer out certain bugs to create a cleaner, smoother, and faster running environment for our algorithm for the recognitions. Alongside that, we wanted to create a method where the embedded system would not sap as much power as it currently does. We have finally come to the end of our presentation. We hope you enjoyed learning and hearing about our design as much as we enjoyed making and designing it. Thank you so much for giving us your time. We are Team 404. Once again, have a great day. Bye-bye. Thank you.